Let's start with a question. Are these two vectors linearly independent? You might ask, what do you mean by linearly independent? So let me put it this way. Can we write these vectors in terms of each other? For example, writing one of them as a multiple of the other one. You might think to yourself that, okay, if I want to write any vectors as a multiple of this one, it must be in this direction. And also for the other vector, it must be in this direction, which is not, of course. So I guess your final verdict is that these two vectors are linearly independent. Now I introduce another vector and ask the same question. Is this vector linearly independent from the other two vectors? In this case, you say, let's see, we already have two vectors and we can span the whole plane using these two white vectors. So if we call them v1 and v2, it is obvious that the third vector can be written as multiples of these two vectors. And lambda1 and lambda2 are the multiples that scale the two white vectors so they can give the third one. So the third vector is linearly dependent on the existing vectors. Now you might ask, what if we change the grid lines based on the first and the third vectors? In this way, the second vector is dependent on the other two vectors. This time we need to scale v1 using a negative real number to get the component of v2 in v1's direction. So lambda1 is negative here and lambda3 is a positive real number. Now, suppose that you have these three vectors. How can we know how to write the third one based on the other two? The first thing you need to do is write the three column vectors in this matrix, which gives a 2 by 3 matrix, and each column represents one of the vectors. If we change this matrix into its row echelon form, we see that there are two pivot columns and the last column is a non-pivot column. If we go further and change it to the reduced row echelon form, we can see that the last column can be written in terms of the first two columns. More specifically, this is how the third vector can be written in terms of the other two vectors, which can explicitly be shown by their components. Make sure to check my other video to learn how you can change a matrix to its row echelon and also to its reduced row echelon forms. Now you might say it's obvious that three two-dimensional vectors are linearly independent. What about more dimensions? For example, these four vectors. Are they linearly independent? We put the three column matrices in a 4 by 3 matrix and then change it to the reduced echelon form. As you can see, there are three pivot columns which show that the three vectors are linearly independent. Let's name these vectors a1, a2, and a3. We can define the linear combination of these three vectors as the sum of multiples of these vectors with some arbitrary real numbers, meaning that lambdas can be any real numbers. The only way the linear combination of these three vectors can be 0 is for all the lambdas to be 0. This is the formal definition of linear independence. If the sum of another linear combination of vectors denoted by b and real coefficients of alpha is 0, but this time there is at least one non-zero coefficient, then there is a linear dependence between the set of vectors. For example, if alpha1 is non-zero, then we can write b1 as a linear combination of the two other vectors, which shows its dependence on these two vectors. For example, take these three vectors. If we form the matrix by the three vectors, this is the reduced row echelon form matrix, and you can see that there are just two pivot columns, and we can write the third column as a linear combination of the first two vectors. Obviously, we can write a linear combination of these three vectors for which the coefficients are non-zero. And we say that these three vectors are linearly dependent. When I say a vector, I'm talking about an element of a vector space as I explained in this video. So if we have a vector space V, and these are a finite number of vectors in the vector space, we can write another vector V as a linear combination of these vectors. This new vector V is also a vector in the same vector space. If there is at least one non-zero lambda such that this linear combination gives 0, there is a linear dependence. And this set of vectors are said to be linearly dependent. On the other hand, if for this linear combination to go to 0, the only possible solution is for all the lambdas to be 0, this set of vectors are linearly independent, and there is a linear independence, meaning that we cannot write any of the vectors in terms of the others. And now that you are familiar with the concept of linear independence, suppose that we have a set of k linearly independent vectors in our vector space. Let's write m linear combinations of these k linearly independent vectors. If one of these linear combinations is 0, then all the lambdas related to that linear combination must be 0, because these vectors are linearly independent. The question is, in what condition can these m vectors be linearly independent? We are going to investigate this question and see an example in the rest of this video. We can compactly write these linear combinations in this form using these series. Let's define matrix A to be a row matrix containing all the linearly independent vectors a1 to ak, and another column matrix containing all the coefficients that give us the new vectors x. Then by multiplying matrix A with each of these lambda matrices, we get one of the new vectors denoted by xj. Obviously, the possible values for j are natural numbers between 1 to m, showing each of the new vectors above. Now we are in a place to check whether these new vectors are linearly independent or not. Linear independence suggests that the linear combination of these vectors equal to 0 must give the trivial solution of all the alphas to be 0. We also know that this linear combination can be written in terms of lambdas, which are the vectors we have formed by the coefficients of each line. This means that the new set of vectors are linearly independent if and only if the column vectors lambdas are linearly independent. Before seeing an example, there is something important you need to know about these vectors. We know that there are m number of these vectors for m number of linear combinations for x's. And the dimension of each of these vectors is equal to k. So, if the number of these vectors is bigger than the dimension of the lambda vectors, they are linearly dependent. Consider these 4 vectors that are expressed in terms of a set of 4 linearly independent vectors a1, a2, a3, and a4. We can form 4 column vectors lambda 1, lambda 2, lambda 3, and lambda 4 using the coefficients that form our new vectors. The next step toward finding out whether these column vectors are linearly independent is forming this 4x4 matrix. By changing it to the reduced row echelon form, we see that there are 3 pivot columns and a non-pivot column. It shows that the last column is dependent on the other 3 vectors and can be written in terms of them using this expression, and shows that the new vectors are not linearly independent. Now you might ask whether we can find a set of vectors by which we can obtain any vector in the vector space using a linear combination of them. The answer of this question is the topic of our next video.